degrees. I'm there.
So we're going to take turns here. I'm going to start by talking about digital biomarkers. I've been working in this space for about almost 20 years, actually, doing the first digital biomarker work with Matt Rizzo, Dr. Rizzo, when he was at the University of Iowa. About us, I am actually a virtual reality loving Wheaten Terrier. And so actually we've been playing a lot with the generative AI for imagery, and Bill actually generated a bunch of images just using prompts. And
yeah, I'm not a huge fan of headshots, and mine is supposed to be a 19th century Victorian print of a man using an iPhone. His Wi-Fi probably sucked back then, but that's what. Yeah, so these are fun. AI is fun, and we want to introduce a little bit of fun AI images. So.
Yeah, we. I don't have any of you played with any of the generative AI like ChatGPT or the DALL-E, the image generation. The DALL-E 3 is out now, and it is really amazing. So, and that's kind of what our talks are kind of going to be around. I'm going to talk about digital biomarkers, and the digital biomarkers that I have worked with have been primarily using consumer devices. And a lot of the work was funded through major pharmaceutical companies. And I'll be able to give you like 2 case studies with, real world data examples and how successful those were. And on the digital biomarkers, just defining them again, we're quantifying health through sensors and wearables, and primarily focused on consumer-based electronics. So Actigraph, I know those guys. They're more, they're not a consumer-facing product. They've targeted primarily the clinical and clinical research groups. And the reason that we wanted to work with consumer devices is because they're practically ubiquitous. They're low cost. The companies like Apple are investing a tremendous amount of money in developing robust algorithms for how they quantify disease state or patient state. But they also, when you're using these, you have the ability to actually access the raw data, so that you can validate and develop your own algorithms. And and that's one of the reasons the pharmaceutical companies are looking at these, is that to be able to monitor patients and develop real world evidence for FDA applications. Really nothing is better than measuring people in the activities of their daily lives. So to develop these types of technologies so that they can be used by people with minimal training, using their own devices from their home internationally, multiple languages. That's what all clinical trials require, is that you're able to support global distribution of your studies. This is, you need to have an interdisciplinary team. And we had some people up here earlier today talking about interdisciplinary teams. I've worked a lot with advanced technology teams that are interdisciplinary. And in order to be able to develop a platform that can be used by patients, usability is huge, because we're not just doing passive assessment, we're actually developing active tasks that align with what people do in their clinical settings. And so we can use that later, I'll talk about it in just a few minutes, to actually provide ground truth to what it is that we're developing and measuring in the wild. So Matt, there's cognition in the wild here is what we're talking about, or behavior in the wild. The teams are typically comprised, in our case, of engineering and data science, because data science needs to understand the data and how it's being collected and the context in which it's being collected. So you need a platform that's going to be able to pull all this data together and aggregate that data. Usually developing a data lake is part of what our platform incorporated. And the things that we did that were very, very manual and a lot of work before become much easier, because these platforms like AWS or the Azure platform that you use here at the University of Nebraska, they have matured significantly in terms of even having AI capabilities just, out of the box. And they have a lot of capabilities in terms of the security needs that you have, being able to run instances of them globally so that you can isolate data. If you're doing like a partnership with somebody, like, for example, I'm going to talk a little bit later about the work that we did with Oxford over in England. They refused to let any of their data come to the United States at all. And so, you have to have an engineering data science team. You need to have clinical expertise, because what we're doing is we're developing assessments that are designed to be clinically aligned. So we're not inventing new, we're inventing new ways to measure patients and the state of patients and the effective therapy. But we're also making sure that it is not so far out there that it can't be used today by clinicians, that clinicians will understand what these measures are and how they reflect patient health and quality of life. And human factors and HCI are really important in this, and design and aesthetics of these types of applications that you're asking patients that may be physically or cognitively impaired to be able to use right off the out of the box on their personal device is key and important to the success of being able to use digital biomarkers in your studies and being able to do translational research for groups like the pharmaceutical companies and industry that we've worked with. So when we talk about patient-centered measurements, we're talking about measuring things like quality of life, cognition, mobility, physical, and voice-based biometrics. Voice is very interesting. It is a rich source of information about health and cognition. We've worked with people. It's interesting for a number of different reasons, but one is it's signal processing. And so it's a totally different set of people that you need in order to be able to analyze this data. But I'm going to show you later a use case where it's extremely powerful source of, and like your physicians will say cough. Some people are just doing coughs, other people are doing where they're doing reading passages or phenomes. There's just a lot of work that what I saw, it's coming from academia, but it's really the pharmaceutical industries that are doing kind of the basic piloting and prototyping with large populations, again, using consumer devices. They do not want to ship devices to patients. You do not want to ship devices to patients. If your patient has a phone in their pocket, and I'm going to show you, we were able to do studies with $75 track phones that collected quality data. It's all about how you process that data when it comes back and what you know about the context of how that data was collected. But we're looking at things like the Oura Ring, which is actually the chief scientist for that group came from the same digital biomarkers group that we work with at Pfizer. So a lot of these people are coming out of, there aren't a lot of people that know how to do this. A lot of these people are coming out of Math Lab. I actually worked with people that were like Josh Kosman. He is now the head of digital and neurosciences for AbbVie. He was also a director at both Pfizer and Biogen. That's actually how I got in there. So Josh told him he knew how to do this stuff when he called me, so I would do it for him. And then the technology side, he knew all the other stuff. So, but we have all these off-the-shelf products now that we can use to measure things digitally without having to have the user do a lot of interaction with them. When we look at things like Bluetooth-based blood pressure cuffs or scales, I've got a CGM up there. People are very interested in continuous glucose monitoring. The Oura Ring, when I get back to that, that is a pretty amazing little device that fits on your finger and is able to quantify states of sleep. They're doing more work with the pharmaceutical industry. They're very interested in something that fits on your finger and is powered for 7 days. So the Apple Watch has to be powered about every day. The Oura Ring can go for 7 days without being powered. So they're looking at usability, like will these people be able to wear these things and use these things out of the box, and will they be able to be robust enough to collect quality data over long periods of time? So it's really important to be able to understand designing for a modular system that is going to be able to address different types of protocols for different types of indications. So you can't have just one measure. Nobody's going to talk to you because they have many different therapeutics in their portfolio. You may find a company that's like a CNS company like Biogen, that they have many different indications that they're working with, but you want to be able to offer services to other companies that have like different areas that they're interested, like infectious disease. And then you need to be able to have a very strong data analysis and modeling capability in your team, because unfortunately the pharmaceutical companies really want to do this work, but their data science people don't actually have a lot of expertise. So they may take your data and give it to another group, but you need to be able to communicate with those people. So you need to have a truly interdisciplinary team, and you need people that I would consider, I consider myself multilingual. Like, I'm not as smart as the doctors in the room, but I can talk to them and understand what their needs are. I can read their papers. I can understand what was the traditional mechanisms. When I work with like a pharmaceutical company, we work with them on conceptual design. I'm going to work with their clinical team initially and understand what it is that was originally the gold standard and why they're not satisfied with it, and what we can do to design something that's actually going to be robust enough to get them data. A lot of clinical trials fail because they just didn't get the data, and the data was just insufficient in terms of its quality. And CNS is a big area for that as well. So, I've done studies and worked with people where, again, this is about a platform that's able to address the aspect of user experience. I've done studies where people have all these devices that they have to open up, use it, and then put it away back in the box, or like open up another application because this application, like there's a really good example of Biogen paid Apple $10 million to do a cognition study. And you had to have a web browser in order to do the cognitive testing, and you had to have a Apple phone to do the other testing. So they had to have two different devices. It made it very, very difficult to keep people engaged in that study. And so we had worked with on, and you should be looking at being able to develop something that is able to have a single user experience, a mobile application that is able to ingest data and be able to provide user interfaces and interaction using a single application that can also be translated. And then when we look at, you know, the output of what we're doing, Matt does this a lot. We develop dashboards, and those dashboards allow us to monitor the data in real time to understand that the data is coming in. We can sample the data. We can know that the data is of good quality. Nobody wants to have a clinical trial or a study, both in academia or in industry, that they collected data. They thought they collected data for, you know, a year, and then at the end it was bad data. They didn't collect all the data that they wanted. And basically, if you miss data in a clinical trial with the FDA, it's considered a protocol deviation. So then they have to do a whole bunch of reports, and so being able to monitor that data in real time, being able to have dashboards that allow the sites to understand the status of the data and the patient experience is really critical and important. So there's a lot of, you know, additional usability work. You want to understand what the sites need to understand with the information that's being provided in the study. And the reason all of this is so important is that we have the ability to collect all this type of data in real time globally and be able to collect this data from different types of populations. So when we started, this actually, version of the slide is by Josh Kosman, who was one of Matt's students at the University of Iowa. And basically what we want is we want to be able to go from high fidelity data that's collected in a clinical or a laboratory setting, be able to translate that into something where at that next step, what we've done is we basically replicated what they were doing in the laboratory setting to a certain degree. And then ultimately what we want is continuous passive data that is essentially giving us the biomarkers, the digital biomarkers that are reflective of what was previously the gold standard in the clinic. So there's multiple stages to this type of research. So if you're writing grants, what you want to do is you have a way that you're supervising the data, you're doing that work in the clinic, it becomes your ground truth, your gold standard, that you then compare these new types of assessments that are very closely aligned to that. And then ultimately what you want is for that data to inform passive measures that are able to, like I think one of your colleagues here presented, passive measures that are able to provide you with a quantification of patient state and hopefully effective therapy. And you can stop me at any time if you'd like, because I know I'm coming completely from left field from academia. So this is like, I know people are very skeptical of consumer wearables and devices. This is the way that the FDA wants to go with clinical trials, because they know that they are ubiquitous. And there are definitely devices that, like, there's companies like Empatica, they make their own device. You know, you have Actigraph, but they're not widely used. They don't have an entire industry and a business behind it. That's one of the biggest challenges, that somebody's going to run a study and they love this little device from this little company. I'm guilty of this, and they're gone. And so if you're using consumer electronics, you have a certain amount of longevity to those products. And, you know, companies like Apple are very aggressively pursuing this space. Google is too. Google has the Verily branch of their organization that is specifically looking at healthcare. And I'm not telling you this because it's like, look, you guys can't do this or you don't do this. I believe you can do all of this. I believe that it's possible for academia to be able to have the abilities that I was able to develop and work with pharma in doing. So, you know, if you look at, you want to do a digital biomarker study and develop very little technology, you can just pull all of this data directly from HealthKit. And this is data that's collected either passively or it can be collected, you know, like through their active tasks, like the ECG that they have. So, and HealthKit can also collect data from other devices and other applications, and it's all aggregated there. So the amount of development that you have to do is an application that just pulls data out of HealthKit. And this is the the variety of data that we can pull. Now, even the activity data that you get, or like if you look at heart rate, we could compute heart rate variability because it was at a resolution, that sampling rate that would allow us to do the computation. It's down deeper into the data, but it's there. So this is an example of low hanging fruit, that it's the challenge is going to be all this data and how you're going to process it and aggregate it. But an application that collects this type of data does not have to have custom tasks developed. It just has to be able to interface directly with Apple HealthKit. And then when we look at like why am I interested, and why are people interested in, the consumer devices? This is Apple. I'm sure that Google has their own version, or somebody else does too. They're innovative. They're looking at the devices that they have and how they can be essentially multimodal, be able to use them to listen to music and also collect EEG. Okay. And this is actually, so we were looking before they could, there's another company that does this, by the way. So it is possible. And I was originally pointed to the other company by the researchers at Janssen. They were like, look, does this thing really work? I said, I don't know. I got to get one. But Apple patented this, and it'll pick up EKG. I'm sure they're going to pick up, ECG. And it's also, it could probably get heart rate and body temperature as well inside your ear, because it's inside the outer ear canal. But we were also using it to look at head rotation and mobility of the neck. So there's a lot that, these little instruments. And then, I'm not a huge fan of like the new Apple augmented reality goggles. I just don't know how big that's going to be in the consumer space, but their other wearables are, I think, going to be around for a long time, and we're going to start to see them become part of, medical dashboards. People need to be able to quantify them. So when we go to the next here, what we're talking about is multiple modalities of data collection. So you can't just look at one aspect of disease. You don't, as a physician. So we have the ability to collect very different types of voice. We can do real-time quality analysis of voice. We've done this on the mobile devices. We can do natural language processing with the voice. We can do signal processing with the voice. We can do on a wearable, not just being able to use those sensors, but what we found to be extremely powerful, and you're all familiar with, is ecological momentary assessment. So if the accelerometers trigger a fall, Apple asks you, did you fall? And that's part of your HealthKit record. We can make our own ecological momentary assessments based on other types of behavior. And then, you have the touch screen and the ability to do drawing, and then the eye tracking and the other capabilities with the camera. So it's a pretty powerful device. And people say, well, it's, Apple, it's $1,000 device. I'm not saying that, well, one of the things I hated was when people sent the patient a phone, because your phone is probably within 3 feet of you at all times. So your phone it's with you. You take it to bed with you. You take it in the bathroom with you. So I'm not a big fan of giving somebody like, here's an Apple phone, because they're not going to keep it charged. They're not going to take it out of a box. I'm going to show you later where we were able to circumvent that. But the quality of even the least expensive phones now have sensors and capabilities. They may not have the accuracy of something that has a magnetometer and accelerometers and like the oscilloscope. I'm talking too fast. My brain is behind. But so when we look at like micro ecological momentary assessments, another one that you can look at is like heart rate. So Apple will alert you if your heart rate, it looks at two things. It's looking at your heart rate and your physical activity level to tell you this seems unusual. It's not giving you any advice. It's just telling you, it's alerting you. So that's what we are talking about, ecological momentary assessments. I want to give you 2 use cases that I consider to be pretty cool and, actually fairly cost effective. I worked on this study with Pfizer, and it was essentially they wanted to be able to collect 10,000 study participants' data in like a year and a half. They actually closed the study 3 months early because they collected all of the data ahead of time. We collected 1 terabyte of voice data. There's an actual link to a video in Vimeo. Pfizer just gave a presentation on this, and it was 70% accurate in detecting COVID. So this study was interesting because they recruited it was completely virtual. We worked with Ochsner as the clinical site that oversaw everything. The application had e-consent screening, as well as it did identity verification through a third party within the application to determine that it's actually you that's signing the consent documents. We had local notifications. The lab kits were ordered through the mobile application. All this had to be used by people of all different capabilities. It was all done initially in the United States. And then what was really interesting is everybody talks about gamification, and gamification is, forget, just you're not going to create a game that actually reduces that releases dopamine like a video game does. But what we did here was we gamified it by paying people on a weekly basis and giving them a daily accounting of did they do their tasks and did they create streaks. And so they didn't pay them much. They had very high adherence to the protocol. They collected data for 40 days where people had to do their daily symptom diary and provide voice samples of both phenomes as well as reading passages. And if you go to that link, you'll see Pfizer giving a presentation on this at a big conference. We are not mentioned at all, which is fine because it was in our contract. And they were able to just with one pass of running it through a convolutional neural network, they had 70% accuracy. And the validation for ground truth with this was PCR tests. So that was a lab kit that was ordered. So this was a pretty successful study. The guy I worked with became vice president of Pfizer when he was done. And I love him very much. He's a great person to work with. So I use the term love pretty freely here. So, and then this study here is a study that I did with Josh Cosman. It started a few years ago. It's out of Ray Dorsey's organization at Chet. It was funded by Takeda, Biogen. Rochester ran the study. It was funded also by the Critical Path Institute. So Merck was involved with this. Roche. And so what we developed was a mobile application because Parkinson's disease is a multidimensional disease, has cognitive aspects to it, has quality of life aspects. So like if you look at the UPDRS, it has like 4 parts to it, Matt. So it's quality of life, cognition, and then movement is a very big part of it. I can't remember what the other piece of it. So it had a lot comprised of movement. And it basically replicates the UPDRS. So we do the quality of life questionnaires. We do voice-based tests as well in this. And then we do cognitive tests that measure both mobility, like finger tapping. We have like drawing tasks. This is the publication. You can, right there is the paper that you can pull from it. And those images are also from the paper. So I designed that digit symbol substitution test. It uses voice. So they wanted to be able to get past people having to draw on the screen that may have fine motor challenges. And so that digit symbol substitution task, that basically you say the number when the symbol is queued up that it actually matches to on the top. And on the bottom, what we have is a fine motor task where a lot of groups have been doing like the pinchy tomato. And we did a task that actually fits more to like what the group pegboard is, where you actually rotate the disc and we call it the Pac-Man task, rotate the disc and fit it directly into the other little Pac-Man. And that is also a very sensitive measure. So there's, fine motor, there's daily symptoms, there's continuous data that we would capture. And then there's that in-clinic piece using the high fidelity sensors. So that would be using the APDM sensors where they have multiple sensors on the body. And that was our source of ground truth when it came to movement. So this was another very successful study. And then the colleague that I worked with at Oxford, Christina, and she has the New York Times just featured her today in what she's doing using movement in Parkinson's disease. And I can get anybody that would like that a link to that article. It's very good about, it's actually better. She makes the claim, she is the physician, it's better than the physician. I cannot make that claim. So here you go.
I have my mic.
Oh, okay. Okay, so I started out with digital biomarkers because this is the source of data that we can now marry to all of these AI and LLM capabilities.
Right. So we decided to make a company to pursue these things because she has a big background in digital biomarkers and health information gathering. And I've been really passionate about using AI to siphon through all this data. And I've been really impressed by some of the advances in AI recently as a way to go and tackle some of these problems. So I'm going to talk a little bit about language models with a quick diversion here for some of the history of AI. Again, we like generating images with AI. These are 4 pictures of dogs using computers in different eras. So I imagined, or I didn't imagine, the AI imagined what a dog looked like using a mainframe in the 50s, and then a PC kind of in the 70s to 2000s, then of course a swanky laptop in the 2000s. But AI is actually really interesting because it's been going on in terms of research for way longer than I knew when I started looking into it. It's been going since the 50s. The term artificial intelligence sort of emerged out of the sci-fi world in the post-World War II era. And computer scientists started to get together and kind of imagine how these systems could be engineered. And in the early days, it was called symbolic AI, expert systems, and they tried to code actual knowledge. So they would take facts and say, put that into computer code, but they realized that was just a completely unclimbable hill because of how many facts there are in the world, and wasn't enough memory to store these in computer systems back then. And so those early efforts in the 50s and 60s kind of petered out. And then fast forward to the 70s and 80s, if you read the research and the history of this, that's what's called the AI winter, where the funding like dried up and the research really wasn't advanced for many years. Fast forward to the 80s and to the 90s, late 80s, early 90s, and 2000s. This is when you had a number of things working together, primarily new techniques involving machine learning. The neural network as an algorithm was starting to be worked on and explored, and also quantities of data were being built, and frankly, just the computer systems were getting faster and more capable at actually processing and storing this data. And then we arrive to today, where deep learning has taken off, and you have a number of factors, but you have parallel processing thanks to graphics cards. So, and any of you guys have kids that have a GPU and they play games, well, the same thing can be used to crunch very large amounts of data. And then you can run these things in cloud infrastructure. So you no longer need to spend millions of dollars building a lab. You can go to Azure from Microsoft or AWS and provision a supercluster to start working on these systems. One thing, my goal here is to make you guys smart. And so one thing I thought was always really interesting when I talk about AI is AI versus ML. They're used interchangeably. ML means machine learning. You guys know what AI means. The way to think about this is that AI is the umbrella term, and machine learning is one of the subcategories of AI. For a lot of what we do in large language models or image analysis, we are using machine learning, and so their terms are used interchangeably, but there's a lot of really interesting subsets of AI. Robotics is a huge one that brings together many different disciplines. Computer vision is the ability for computers to see an image and recognize it as a cat or a picture of a dolphin. Natural language is the ability to understand speech and text. Speech recognition is more audio, and semantics is the ability to understand the context or the meaning of words and language. Hopefully you can read the code on the left, but it's code, it's normal computer code. And I wanted to highlight this because one of the core differences in the AI system is an idea of a model. And that's a little bit different than an algorithm, even though an algorithm is a conceptual black box. You put something in, you get something out. Same sort of thing happens with a model. But the biggest difference in traditional computer systems and technology systems, as represented on the left side, is that it was traditional programming, procedural, if, else, conditions, and you could write test cases that could test every single branch of it and it'd be functionally complete. Models, and we've already seen an illustration of this in a prior talk with the neural network in the middle, those are probability machines. They're not giving you an answer that the picture of the cat, they're telling you with 97% probability that it's a cat and 3% that it's a dolphin. And typically those systems are represented to users as this is a picture of the cat, but underneath everything, it's a bunch of statistics. And I'll explain a little bit that later. That's the biggest thing to kind of realize what's happening under the hood in some of these AI models. And then we get to large language models, which I know you're all familiar with because I'm sure many of you have been using ChatGPT to write grants or anything. Maybe nobody will copy that, but that's okay. But for those of you who don't know, large language models predict words and sequences. So you guys are going to help me. If I say twinkle, twinkle, you say
Little star.
right? If I say Mary had a little, right. So that's essentially what the large language models are doing, is trained on vast quantities of information. And so instead of being coded in advance in terms of facts, these models learn from data, and so they see associations. And this illustration is actually from a fantastic article on the Financial Times. I have a link to the URL, but what it's doing is it's taking and completing not just words, but like looking at the most appropriate sentence to finish the phrase with in this case. But that's what it's really good at doing, and it learns that by ingesting a lot of information, in this case, terabytes or petabytes of information, and looking at patterns of words, right? In this case, more than just a print product is likely what is seen in past contexts. And that's why, as a quick diversion, our talk is titled 1 + 1 = 3, which is kind of a funny nod to large language models. So if any of you know about ChatGPT, it's not very good at math. And that's because maybe it knows the answer to 1 + 1 = 2 because it's seen that as many patterns in its training data. But if you give it two extremely large numbers and tell it to multiply it, it's going to give you the wrong answer because it hasn't seen that pattern before. So it's all very pattern based. And what else? Okay, so besides being able to really to predict the next word or sentence or paragraph, these systems are excellent at understanding semantics and they're excellent at classifying. So you could take, for example, the entire database of clinicaltrial.gov, put everything in there, and you could classify all the studies based on the disease it looks at, the condition it looks at, the device being tested, or whatever else, as a condition of just having gone through a large language model. So I'm going to skip a lot of the math. I think it's really interesting. I am hilariously not a math major. I was a computer scientist with a almost math minor. That's my only claim to fame in mathematics, but I can appreciate the math under the hood. And so there's a lot of science behind how words are translated into numbers and how numbers are associated semantically. But the thing you kind of think about on the left side here is clusterings of terms. And so through its training process, the large language model could understand that, oh, football and soccer are semantically similar. I and we are both pronouns. Pronouns in our site semantically similar. Sea and ocean, same thing. Take that in the medical context. It would sort of understand that acetaminophen and Tylenol are similar things semantically and as well as obviously medically. And so this picture here, and by the way, here's the URL for this FT description. It goes through really wonderfully and explains some of the inner workings of a large language model. But under the hood, these color bands are what's called an embedding. That's what's stored in the large language model. And so there's correlations being done and a lot of math applied every single time you're predicting the next word. But this forms the basis of why these models can understand language at such a high level. And I think we've seen an illustration very similar to this. And I find it pretty rich that a computer scientist is going to talk to people who study the brain and talk about neurons, but here we go. Essentially, it's somebody made a comment earlier that we don't actually know what's happening in the systems. That's not quite true. We know what's happening in each individual neuron, that they have evolved through training to understand and identify certain parts, but it's the collective whole action that is a little bit opaque to researchers at the moment. But basically, you have inputs, you have outputs, you have layers in the middle that do a lot of computations, and then out of that comes a probability of a certain next word or a certain image classification. The network works together just like the brain does and is modeled after how we think and how we learn. The last sort of nerdy topic I would leave you with is this is called an embarrassingly parallel problem, which in computer science means you can parallelize the hell out of it, which means you can do these things much faster. So again, we've evolved to a place today where we can pour through terabytes of information in split seconds and make some really interesting results with that. So the way to think about these things in practical use, if you're looking at it in terms of research or whatever else, is that language models have a base understanding of language, and language can include computer code, it can include scientific information, and that's what I would represent with the innermost circle here. One of the interesting techniques is taking other additional knowledge and augmenting a base model with that, and that's called fine tuning. And so you can ingest information because most of these models you've read about, they take months to train. And so it's not like real time. You can't ask, did the Denver Broncos win this last week? They did not. But yeah, sad. But so they're not up-to-date information. It's not like a Google search engine. But there's other ways to augment information in. So we're looking at ways of taking current information, current research or whatever else, adding that to a base language in terms of in a fine-tuning kind of manner, and then using that to drive insights in the healthcare world. This is months old as a technique. The world of AI and this kind of stuff is brand new. I think it was about a year ago that ChatGPT even came out. And so things are changing and evolving at a breakneck speed, but it's been really impressive to see this so far. Okay, and then a couple more thoughts, and then we'll talk about the world of biomarkers and AI together. We think that something like ChatGPT, I use that as the kind of catch-all term for large language models, is appropriate and useful in the medical space because there's such vast quantities of information. And I think one of the best ways it was explained to me is, you take the best physicist in the world. They're not also the best chemists, and they're not also the best astrophysicists, right? These models have the ability to correlate vast quantities of information together in a way that drives a lot of productivity, drives a lot more insights. And so we're really excited about the stuff they could do in that world. You've probably also heard about this idea of hallucinations, which is when a large language model is confidently wrong or makes up facts That's why we actually title this 1+1=3 to kind of take a jab at some of their abilities to make things that are factual, but there's techniques and systems we're learning to put into place to control that. Not everything has to be a direct interaction with the user. We're looking at systems where you could analyze large quantities of medical information and then show that analysis to the user after it's been verified by humans. Our vision is that a lot of this stuff really helps people do their job better. And so this is assistive technology, not something that would replace a human judgment. Okay, let's move on to the next part.
First, any comments or questions? Because I said a bunch of things that are sacrilegious in a lot of research groups, saying that you can use these consumer devices and that this type of work is accessible to academia and not just to the very wealthy old pharmaceutical companies. And then we'll get into like what we think we can do with all this. Did anybody have anyone want to shoot the messenger today?
I have a question, and Jonah, it's really encouraging to be able to use real world devices to extract data that's clinically meaningful. And you talked about the complexity of using different platforms and that people have limited access to apps and phones and the internet. I wasn't sure exactly what you were proposing in its place. Was it one single device to cover everything, or?
No, what you need to do is you need to create essentially a modular based system so that you can build applications for specific clinical studies. But you want it to be that you're only using one application for that specific study. Some people in the clinical trials industry, they create a universal app, but then it's very, very narrow. So what you want to be able to do is say, like, we created modules that measure, can be used for measuring voice or cognition, and you put them together, but you need to have a framework, which can be done, that you have a single application for the user. So the user knows they're in your study, they open the application, it has all the security, they did the consent and signed on. When they open that application, it lets them do all of the tasks that they need to do that may be active tasks, or it collects all of the passive data. What we've seen and what I've seen in a number of studies is it's like, go get this device, open this application, now go get your glucometry and go get this one. And what we have found is that just is too much for somebody, especially if somebody who's sick or is on medication. And so we need to look at, and I was very focused on this, is how do you create a user experience that's able to integrate all the different data sources, which you can do now because a lot of the sensors and manufacturers have APIs that you can pull the data either locally or through accounts, pull it off of their servers and then integrate it onto your servers. So, and we have done this so that it's all HIPAA and GDPR compliant as well. So there are ways to do that. People, oh, you can't do that. It's just like, yes, you can. So, okay.
So part of the modular data is interpreting it in context, right? So
yeah.
Your voice analytic machine interprets me screaming in a football game.
I'm not recording.
I'm being mugged.
Yeah, no, but those are good examples. So like if I had an application that was called I'm being attacked and I turn it on, I will know you're being attacked and I would be able to distinguish if you're being mugged or if you're being, whatever it is that you're at a football game. So so when we talk about passive data, we're not talking about voice data. Passive, it's absolutely a problem. That was like one of the problems people were trying to use Alexa to collect voice data from patients. It's just, there's too much context there. There's too many people. There's all this stuff going on in your background. You've got like the radio playing and stuff. What we talk about is like, when we're talking about voices, go to a quiet place, just like you would ask them to do if they were doing like a survey. We want you to go to a quiet place in your house. And we actually do a calibration routine to see if there's background noise. So we do a signal to noise ratio calculation to determine how many decibels we need in difference for the noise. And then we tell you, you can't record here, or you can. And then we record the voice. We also collect and from multiple devices, you can control the frequency at which the audio is being collected. There's a number of different things that you can do that the phone manufacturers provide you at the operating system level to collect. And then we can also know what the sampling rate was for the audio that was collected, as well as what the CPU and the processor was, and the model of the phone. It's all in the phone. So when you're doing this type of like BYOD work where you're collecting data from people's personal devices, you have to be able to get consent to collect all of that data so that when you're doing your analysis, you have context of the hardware and you understand, what type of device and what type of microphone and frequency was there. So voice is in what we would consider captured doing an active task and not passively. So I'm not
And
like
I understand. I just trying to put this in the two-dimensional graph of fidelity versus control. So you have more fidelity because you're collecting world and the data on voice in the real world. It's the real world. You're constraining it a little bit because you're making it quiet and having a person, sort of speaking. They're not doing anything that's sort of engaging in any kind of social activity or anything like that. So it's got a little bit less fidelity, but
No,
there's a trade-off.
it does have fidelity because I am replicating what you did in clinic, not your everyday life. I'm collecting it at
Right.
home in those states. But so what they did with this study, the voice study, they then worked with a clinic in the UK and collected data just in clinic. And they now have that clinical data. That's why I was talking about, you want to have your clinical data. This is like, we know exactly what context is. You want these active tests, and then eventually you'll get to hopefully having digital biomarkers that could be completely passive. Even here is a tremendous amount of value.
Yeah, no,
Because
this
I
is
can collect
great.
much more data and I'm no longer geographically bound, and I can provide access to people
And I know
of all races.
the military is interested in these kind of things when they're looking at war fighters who are engaged in combat and trying to figure out if they're healthy, if they've been wounded, if they are distracted under too much information. The voice changes, for example.
Oh, okay.
Yeah.
So that is going to be tough because you have to understand like what that background noise is to be able to segment it out. But that's why the people that we work with people that were voice experts, that they have acoustic engineering backgrounds. They can, they know all of the different, everything that's in the, I don't know if it's a histogram, but it's basically, there's all these bands inside the recording that they can segment into, like, this frequency is your actual voice. This is associated with this. So it's not, I'm not an expert in it. Most physicians won't be an expert at that level, but it's pretty amazing what people can get out of audio and being able to extract data. So it may be in that case, like with the military, you would bring somebody in that's a signal processing expert that could help us to be able to understand how to segment that audio recording.
Thank you. I think there was a question.
Yeah, is this on? Yep. Oh, thank you so much for your presentation. And I think there's many of us in the room that you don't have to convince at all that we want to use these devices in this way. We've desperately wanted to do that here for many years, but we don't have anyone here like you.
I'm adjunct faculty now.
All right. Okay. All right. Excellent.
No, I'm-
And I'm an honorary doctor, so.
Yeah.
Okay.
Doctor.
Well, kidding aside, what we have really struggled with is getting the data out of Google and these sorts of things and getting through the contracts and creating what you call data linkages and these sorts of things that we just have never been able to get by. So I was just going to ask the powers that be in the room, since Human True is here, does that mean that they are an approved vendor by our IT security? And
Probably never.
if not, why not? Well,
Your IT
we need to hire
Yeah, yep, no,
somebody like this company to help us facilitate our research, because we have multiple researchers basically abandoning their research because they can't get through all the individual contracts and the dashboards and the linkages and all this with these companies all on a single investigator one-on-one sort of thing. It takes too much time. You get a grant that's only a couple years, you can't do
You
all
can't
this.
build all that. You have
You
to
can't build all
you have
this.
to have a framework. And that's why
So
I
we
find
need that. Well, we tried to build a framework and we didn't get any further than we couldn't get to that dashboard phase that you talked about, and we couldn't get the data linkages set up, and then we got stuck in contracts. So the powers that be in the room, this is just a plea. Please help us. Please make somebody an approved vendor that we can get this.
Well, that's what we're hoping to do with this informatics group that Dr. Rizzo talked about at the beginning. Not only a physical space, but have all the processes, or as many processes as we can.
But we needed
already
we
approved so
needed
that-
it yesterday.
Yes, many times over.
Excited to talk about these capabilities and like what could be done you know, for example, your entire backend, from what I recall before, is built in Microsoft using Azure. And they actually, I actually retired. I went to the Microsoft conference in Seattle last May. My husband was like, "Oh, you should go." I was so sad. I was like, "Your dad was like you," and I actually cried at the conference. I was excited, and it's because they had the presentation there with their CEO and OpenAI. And what's really interesting is they said their new CTO came from, I think, he didn't come from Google, he came from like LinkedIn or something. Microsoft, so OpenAI owns all of the ChatGPT stuff, but Microsoft has an interest in a lot of it because they provided them with the money to do the computing to create the model. And so it was a couple $1 billion or $1 billion. And the guy, their CTO said, like, many times we didn't even get good work because it kept churning and churning. It was like, oh, it's worse than it was yesterday. And then finally, it like just settled, and it was a good model. So a lot of this stuff is really brand new. Like in the last year, that you have large language models, and then when they released it, they had no idea that everybody in the world would actually find it interesting. And it's because it was natural language; anybody could use it, and it would give you interesting information. And you didn't have to. The interface is basically what Google was when it came out in 1999. It was just a little chat bar.
Yeah, I think before we take our next question, I think one of the reasons we decided to make a company in this space is because we're really both passionate about, getting technology out of the way. In this case, in the medical research area and other businesses we worked with before. And it's really frustrating to me as a tech guy to see technology being never had more technology in the world, but just no ways to really meaningfully deploy it at scale. And so I think AI is seriously as big of a change in the world like that the internet was back in the 90s. And I think that that's going to usher in a lot of change, a lot of efficiency, a lot of more natural ways of working with technology, and we're excited to help. Speaking of technology,
We don't want to go over time.
we have five more minutes.
Okay.
Thank you for your presentation. Very interesting. I've done some work on building a single dashboard with catching the biomarkers that you're talking about for first responders. And we also have built in a feedback loop so that they are aware of what their situation is when they're in some kind of a emergency situation. I was wondering, in your studies here, I didn't hear much about the feedback loop back to the clinician, back to maybe a caregiver, or actually back to the patient. And is that part of your that you do that as well, or is that been a challenge and so on?
So once you have an infrastructure that's built where, we have data that it can essentially be used for many different types of services. And so like when you talk about a dashboard or some kind of alert to a caregiver, like in the case of like maybe an Alzheimer's patient or like if I knew that my dad fell, that I could be alerted on my watch that you need to call your dad or call somebody. That is really dependent on that data layer and how that data is exposed to like different types of services that you produce. So the dashboard is really a byproduct of what you architect underneath it and the understanding what the information is and the utility is. So
Yeah, I think traditionally the dashboards you've built have been for the clinical researchers, and so that hasn't been the means or the need to loop back to the patient. But what she's saying is, yeah, absolutely, the data is there to do that. And in fact, the more these things get entangled with AI, one of the core patterns is giving back to the user, hey, did my suggestion to you, was it a thumbs up or a thumbs down? And those signals back into the system help train models and kind of make a better loop of performance. So I think it will become more commonplace.
So I've heard a lot of people talk about dashboards as being horribly hard to do. They're not if your data's in a good structure that you can actually, pull from it. But like I made dashboards with Matt, like for his driving research, where he could know which devices are online, when the last time a device was collecting data, when the last, how much data is coming across, all of that. So it's really about having people that know what they're doing. I know.
Frankly, it's true, but like I think a lot of dashboards are perceived to be hard. Technically, they're not. You just need to have the right engineers behind it. And thankfully, actually, AI. I could talk forever about AI helping software development. That's a huge problem.
Well, just one other comment. I think that to have the patients engaged and to stay with the trial or whatever is that, again, the benefit back to them to get some feedback and maybe on a more real-time basis than to wait to get to I don't know, I just think the more they get the feedback, the better, and caregivers.
For their time, it doesn't have to be, it was not a lot of money. I mean, like, they were getting like $1.50 a day it's for their time. It's not, they're not making money, but you're asking them for their time. And with systems like Greenfire is the company that will pay the patient in near real time. You can show them that I did all my tasks this week, and look, Saturday, there's money in my account.
Well, then also one of the things that Joan has really excelled at in the past has been just engagement of a mobile application. I mean, we know that if you're part of a study and you're told to use your device, that, you know, as dry as medical research is, you're competing with Candy Crush and LinkedIn and Facebook and all the other distractions on your phone. And so a big part of the work you do on these things is a good user interface that, you know, doesn't suck and is easy to use and is engaging.
So if I could build on your comment about user interface, because that gets to the question about the patient experience.
Mhm.
Yep.
And there's sort of two levels of question I have. One is, as you have worked in this space, how have you developed feedback about the user experience? What works and what doesn't work? That's sort of level one. And right following that is my question: how different are different populations?
Very.
And so then
You're answering the
the
second
third level after that is,
There's another one. Okay.
how do
Did you
you
say it's level 3?
how do you deal with that?
Yep. So
Well, real quick on number one though, like that's so anytime you use any application on your phone or on the website, well, there's a lot of instrumentation behind the hood or behind the scenes. So, you know, you ask any modern software development team, how do they know if their application is working well? Well, they can see not privacy guards, of course, but they can see what you're clicking on, what actions you're taking on, and that stuff is instrumented to know if the goals of the application are being met. And so that's some of what flows into these applications as well. Like we could tell, is the user having a hard time completing something? You know, you kind of look at it, do they fall off the finishing the form? There's all these actions that could be
but
instrumented.
before all of that, like when I worked with the pharmaceutical companies, we would work with focus groups with the different clinical populations. So even like, I think Cedar Sinai went to a conference, they work with their cancer patients to make sure that their applications are usable. So there's a whole process around usability and user experience. And we would work specifically with clinical populations. They would bring people in, like we did one for patients with Friedreich's ataxia. And we developed the application so that it would be both vertical in portrait mode, but then there were some tasks that were in landscape mode. They couldn't rotate the phone. And so we had to redesign the user interface so that it was always in landscape modes and some of the things that actually needed it. So we will typically, with a specific clinical population, work with them on making sure that we address some of the, the functional capacity of the patient population. And then that's where the HCI human factors stuff comes in, is like having enough people that are giving feedback and then incorporating design that addresses it. And then that was what was
Third question, right? Third level.
So I've already forgotten. I'm down to level 6. As you identify differences in different populations, and if you're targeting patient group, that's already, in my view, that makes your job easier.
Mhm.
But you're looking a little bit more in a population base. When you get to groups that have different approaches to using technology or different types of relationships with healthcare, have you thought about how you address those differences through the user experience so that you're aiming toward equity rather than reinforcing lack thereof?
I think if I may, this is a sort of long way of answering your question, but like if any of you guys have used ChatGPT and you've done things like, you know, pretend I'm a 3-year-old, explain astrophysics to me, right? And then it gives you back an answer made on a 3-year-old, but like a third grader, and explain astrophysics to me. It'll give you a different answer than saying I am a PhD level astrophysicist, right? It'll contextualize the answer it gives to you. So I think one of the things I see down the road as becoming commonplace is tailoring user experiences based on the context of the user you're looking that's using the application. And you see this a little bit today, like if you use an application, you store your preferences, it kind of knows maybe some things about you. But in general, I think you could take that with the scale of AI to a much deeper and more fine brain level to actually modify the user experience, the data you're presenting to the user, the way in which you're talking to the user could be tailored on the fly. These are things that traditional application design hasn't really been able to do because it's a lot of work. But with AI, you have a system where you can do that at scale super easily. And that's one of the things that AI systems excel at. So I would see that.
And then talk all about large language models. Unfortunately, everything I've heard and read is in the one language I understand well, and that's English. Do these exist for Spanish, Mandarin? And
They do,
because
yeah.
the context is quite different.
They do. It depends on what it's trained on, but if you feed it a bunch of information in Spanish, it'll know. I think researchers have found that there's an emerging understanding or a translation ability in some of these models, and I can't really explain why, but I think it has to do with just understanding at a semantic level what the meaning of the words is, and then being able to translate that pretty easily to different languages. But a good example is that like these models excel at computer code, which is a form of language. With enough training data, they are unbelievable at computer code because it's highly structured.
We're using it to write code for software now.
Quick question on the sort of cross-cultural use of these tools. One thing that came up just now is translation. And one of the things we struggle with clinically is translating from English to Spanish to Vietnamese to some dialects of Burmese where the context is different. It isn't enough to get the words right. One needs to get the context right, and one needs to convey the message in a way that is culturally understood.
Right.
Yeah, so
It's a really complicated
yeah,
problem.
so what they do, Matt, is they use companies like TransPerfect, and they do what they call forward and backwards translations. And so TransPerfect, so you build your software so you can basically plug whatever languages are the strings in that comprise your language. They also have to be able to accommodate left to right and right to left because some languages are left to right.
So they're continually checking for feedback on the accuracy of the translation and then redoing it with the feedback and then.
Well,
No,
no,
they
yeah.
send it. So TransPerfect is the company. They do it like for books and all the companies that have big products. You send them essentially all your screenshots for what you have to have a screenshot generator of the application in English. Then you send them, you have somebody actually translate it. And then what they do is they do a forward and backwards translation. When they do the translation, they send it to another person that is a native speaker in that country where they're going to, with that potential demographic, like education level, and have them translate it back. And it needs to have the same meaning as the original English translation.
So that's great. But when we're in the clinic, we have to work like right now. And we have somebody who's got some urgent problem. We have to convey back and forth. We may have a relative who maybe speaks a little bit of the language, but doesn't understand the medical aspects of it. We may have a translator who we have to get hold of on a phone to some services in Houston or something like that. And they are a little bit disinterested and they may not understand the medical context. So it gets to be a game of telephone. And it seems like the large
There's
language
a
model.
potential here to
Yeah.
be able to do that.
It's going to completely change all the translation stuff. I mean, I think
TransPerfect's going to be in big trouble.
it's going to be
That's how it's currently
it-
done.
translations in 5 years are going to be 10x less expensive, 10x faster. And already today, you could embed something in the application, like install Google Translate on your iPhone, and then you can speak to it, and it'll say what you said in English in whatever language you want, including Klingon, believe it or not. So it's remarkable that technology exists today. It's only going to get better.
And like, if you look at like something, like not just translations, but like all the other service, you just embed services into these applications. So list the problems that you have, and there's going to probably be a service. Like, for example, this thing can ChatGPT, the latest thing, it can see and hear and speak now. And you're like, no, it can't. And he will show you.
It'll steal your girlfriend. It'll drive your car. It does all kinds of things.
Well, it'll marry your daughter. No, it's which sounds like this is not like I don't own any of the stuff. I'm just saying the stuff is coming very, very quickly. Like there's a company called Wondercraft AI.
Wondercraft, yeah.
You can listen to a podcast. It sounds like it's from NPR. It writes a podcast and then it actually narrates a podcast and produces it with music behind it.
She's mentioning this because we think you need podcasts in your trials.
I think you need,
Anyway.
no, but what I'm saying is that the natural language capabilities of actually speaking are very-
Unbelievable.
are
Unbelievable.
incredibly mature. you can train it on your voice mat so that it could be Matt Rizzo doing the podcast.
Which, I mean, it's just, again, it's kind of funny to think about that, but like,
Just look it up, Wonder.
well, yeah, Wonder, I forget what it is, but
I think it's
the
Wonder.
big picture is that I think ultimately, like, you could have an onboarding function, that's user or patient facing, that feels like you're talking to the researcher themselves, or like their, you know, trusted doctor or whatever else in a very colloquial voice, and
And people ask
very
me, "Well,
natural.
What are you and building to do? It's like, oh, God, we got to figure out what we don't want to do. It's like, and we want to find people we want to actually work with. So that's why this is a very, it's developing really quickly, Matt, in terms of like what other people are applying. Microsoft and some other companies are working with Epic to be able to create, you know, all these tools for doctors so they don't have to, that their billing notes are summarized and all that type of stuff. I found it interesting. Nobody's looking at nurses very closely, and I think nurses have the greatest burden in care. And we actually did some stuff playing with that.
We have time for one more question. Okay.
Yeah, one more question. Now I'm going to quickly show you the.
No, actually, we're good. I mean, this is sort of our,
So we can
was our
talk to you
son,
about
but
the
we-
things that we've already integrated and tested, and what we think is going to happen. If you just boom, boom, two more slides there.
let's take our last
Yeah,
question.
go ahead.
Okay, yeah, I actually have a big question, but I only ask one, and the other I will ask you later. So, so my question basically, for clinical trials, many years ago, I listened to some biostatistics department faculty talk about, if I remember correctly, it's about like 2/3 of clinical trials in a typical place actually never goes to the real sample collection. And many also they fail, not necessarily they fail, they stop somehow
Yeah.
in the middle of it. So my question here is based on what you learned here, if you collect all the clean trial gov, or many other large data set and train it here, can you go through your prediction to basically say, okay, this kind of unfinished clinical trial, we should recommend to continue, and either through the internal funding or maybe industry, that will be potentially save a lot of resources because they already were started, they may be in the middle. I just wonder if your
Yeah,
system
there's
you can do that.
There's a couple of challenges with clinical trials, right? So there's phase 0, 1, 2, 3, and then 4 after it's been approved, right? So
Right.
what you're describing is that they define the endpoint when they design the study, and then if it doesn't look like they're going to actually achieve that endpoint, they'll cut it off early. They'll just say we're done, and then they never look at the data again. And that's pretty criminal because they're not going to let anybody else look at the data either. I think that this has the potential to maybe look at, maybe we should be designing clinical trials differently and being able to look at how the information from the clinical trial could inform the next design of the next clinical trial. So that's part of like where we have this benevolent love circle with data, and that what you're going to see is that data is going to start to inform design, and it's going to go very, very quickly where the AI is going to help you to determine a better study design or potentially different result. So that's part of the problem with clinical trials. They define the endpoint before they start the study. They designed it maybe 3 years, and then now ahead of releasing the study, and they now have better ways to measure it, but they still use the old antiquated. I'm particularly annoyed at how CNS disorders are measured using subjective and very blunt instruments. So that's why Parkinson's disease and movement disorders are so compelling, is that we have quantifiable measures using things that people understand, like, inertial measurement units. So, okay, yeah. I thought everybody could hear me on the planet when I talk. So was this helpful in terms of your answer, that question? Did that answer? I am a
If
optimistic.
it works, it's saved like $1 billion, right? Because many clinical trials, they may finish, stop somewhere.
Yeah.
So my point is, if we can reuse some of the clinical trials and show the great potential, that may be, a lot of cost saving.
Well, we
They
talk
finish
about
somewhere for
because-
many reasons.
Yeah,
There's 480,000 trials in the government database, and associated data sets. I think not all the data is usually published, unfortunately, sometimes. And so I don't know what that takes. If that takes the companies or the researchers doing the trials to release more of that information. But the good thing is, if that information's out there, that can be vacuumed up into a learning system like a large language model, and then be put to good use. So I would hope that that's one thing we can contribute.
And from the biostatistics side, I was telling Matt that like simple things you can now, instead of writing SQL, you can just ask it. You can give the data to it. You can drop a CSV file into ChatGPT.
Yeah.
It's got a plugin, and you can interrogate it using natural language rather than SQL.
I showed him that this morning.
Okay, wasn't that fun?
Yeah, yeah, thank you, thank
Yeah,
you.
thank you.
John, and,
All right, I'm done. All right, there you go.
Okay, anything else? Is that, are we out of time? Oh, okay.
Oh, we're not
Yeah,
out of time.
we can just-
Oh,
okay.
then we get to talk now about digital biomarkers. Yeah.
Okay,
Yeah.
well, yeah.
Okay,
so-
Bill, finish. Go.
Okay, I mean, this is, so what we're trying to do with this, with the basis we gave you a little bit in digital biomarkers and large language models is to conceptualize some of the possible intersections of those two worlds. These on the left, I guess, are some of the things we've been looking at from a research point of view and trying to figure out like what's the value we could be bringing to the world. We've been experimenting a lot with synthetic patient records. There's a great project called Cynthia on the upper left there that allows you to generate, you know, in numbers of patients. So we're talking about a full,
1,000 patients in how long?
oh, a minute. Okay, right. So let's say, let's say you want to study, well, there's lots of different uses. I'm trying to pick the one that comes to the top of mind. For us, you know, we are looking at working with researchers in the future and actually reading actual patient records, right? Patient records are hard to come by. Obviously, privacy concerns are a big deal. Right? Right, and I don't have access to them, or we have to go through a lot of paperwork to get access to them. But the reason you have synthetic data is you have, this is eventually data that can help you build data pipelines. It can help you model user interfaces. It can help you train AI models. It can help, you know, understand the art of the possible when it comes to using this stuff in an actual application.
Give an example of what's in Cynthia.
Right, so synthetic data from a patient point of view, it's a full medical history. So I could say, give me 1,000 patients from the state of Iowa. It'll give you something that represents the actual demographics of Iowa. It'll give you a bunch of patients that have been deceased. It'll give you a bell curve distribution of patients over time. It'll give you the full medical history. So this person had childhood asthma, was it treated, how much did it cost? And this delivers it to you in a format that you can easily ingest, like a CSV file or a FHIR record.
No, it'll make a Matt Rizzo that is 55 years old. It'll have his clinical visits synthetically generated over a certain period of time, and then have like if we wanted to say Matt Rizzo, I shouldn't use Matt Rizzo got rheumatoid arthritis at this stage. It'll have the model for rheumatoid arthritis and what the symptoms would be and what the treatments were. It'll synthetically generate a patient and all of their clinical visits as well as all of their treatment.
One of the things we could use for too, this is kind of interesting, is you could take that population. So we've noticed the clinical trial database for one thing. Obviously, you guys are familiar. There's very nuanced inclusion criteria. And so you could run queries over a synthetic set of like 1 million users, find out at a very nuanced level which ones match in. And that's not just a simple like, is the patient greater than 18 years old or less than 45? But using a large language model, you could actually cluster people, you could actually understand the inclusion criteria semantics, and then match it up with the population. So the uses of that, as we could imagine, are people writing studies and say, you know, what kind of population would be applicable or enrollable in this kind of study, and then tweak it based on that and test it.
Yeah, it's
Somebody actually did that with the COVID in Massachusetts in early like April of 2020.
there's a
They started modeling it and trying to predict, you know, what's the spread rate, what's the cost to the government to treat it. Yeah, so basically, I think the idea is anything you can do with patient data, we can make the data in a synthetic form and then use that as a test bed or to develop algorithms or whatever else.
Free to use. A digital twin has an actual person associated with it, and they're both modeled to be very similar. so that you can actually have an arm that's synthetic and then have a fewer number of people that have said, this is a twin, this is how they in the model responded to the drug, and this is the patient. I believe that's what it is, because there's.
I think those things are going to converge over time too, because I think the systems that have made synthetic health records will get more sophisticated and more AI driven, and will model what actual people have done in the real world. The digital twin would be kind of the ground truth in that
It's kind
case.
of crazy because Cynthia was developed by MITRE. It's open source. You could use it at the University of Iowa. You should, it was developed by MITRE and I think Mass General. And they originally built it. You can download the entire data set for the state of Massachusetts that they built for their analysis. So you can develop your own data set just in seconds if you, download the application. And it's got a user interface, but we actually, play with all the source code with it. We need the row, we need Bill and so this is just one example of, like, you just asked a question about something that you would not have been able to utilize or access and then be able to easily integrate it with other things without all of these LLM and AI capabilities.
Yeah, we're just, I mean, this slide probably doesn't do justice to the full potential of these things. I mean, we're just starting to scratch the surface on the actual uses of these things. Clinical trial protocols and developments. Oh yeah, sure.
Input,
And then this
and
one,
then
yeah.
this could be output.
Yeah.
And so. Because it'll become a feedback loop, because when you start to use it, you'll be able to train it better and be able to create better models from it. But initially, it has a lot of value for research in particular. It's not going to replace a doctor. The other things that we've been looking at is utilizing these tools to be able to train what we call co-pilots. Like, somebody asked us, there's companies that actually mine. There's companies that actually mine clinicaltrials.gov and then sell it to other people. Why would you need somebody to do that if you have a co-pilot? Like, he's already got an interface that looks like Google, that you can just ask it yourself without having to go through all the screens. So that's where you can now start to hook up things like an LLM to another data source and use natural language to interrogate it rather than going through all the little forms and screens to do stuff. Because if it has an API, it can do it itself underneath the hood and look very intuitive and natural for somebody that is a layperson to interact with.
Okay.
I wonder if you could give us a few closing remarks, and then we want to give people a chance to
I think
stretch and
Bill
take
was
advantage of. Pardon?
Yeah, Phil's gonna talk, yeah.
Oh, okay. So I want Bill to talk. So,
Closing thoughts. I mean, I don't know. We're very passionate about this. Again, like, my interest with technology in the past, and I've had a software company before, but like, I'm very active with nonprofits because I believe that there's so much technology in the world, but like, especially smaller nonprofits have absolutely no way to deploy it, and so it's rendered meaningless. And I think in healthcare, I see the same sort of potential problem, and I think that AI represents a brand new way to interact with computers in a very natural way. I think it's going to be revolutionary for sifting through large piles of data and correlating different diseases or treatments or medicines. That's personally why I'm here. I think it's to a large extent why Jonah is doing this stuff too. So we're very excited by this world. There you go.
Thank you very much. Instead of artificial snacks, we have real snacks
oh boy.
outside, and if we can reconvene in 10 minutes at a quarter to 4
Thank you.
for another presentation. Thank you. He doesn't understand.
You're welcome. That's great. Oh, no, no. We were talking.